Hi everyone, so today we are going to look at AC circuits, and I assume you have already gone through the previous two set of slides which were on the introduction to sine waves and a review of complex number theory. This is uh, These were not comprehensive reviews. You should have already covered this theory in other courses and in your secondary school course of study. So I was just giving you the salient points that you'd need to go ahead with this section of the course. So by the end of this session, you should be able to calculate steady state sinusoidal voltages and currents in RLC components and explain the utility of using the phasor domain for steady state AC analysis. And we'll see what the phasor domain is in a little while. So if we look at this simple RLC circuit, we have a sine wave source driving the RLC circuit. There's no switch, so we could assume that it was closed for a very long time and all the transients have died out. Now, since the voltage is constantly changing and also the current is constantly changing, then when we look at the VI relationships for the inductor and the capacitor, then the di dt is no longer zero because the current is changing. And similarly for the capacitor, the dv dt is no longer zero because the voltage is constantly changing. So we could no longer assume that these two are zero. So we cannot approximate the inductor to a short circuit and the capacitor to an open circuit. These would be wrong here. So if we do want to calculate what is the voltage or the current, let's assume we have the current and the current is in the form of IT is equal to Im cosine omega t plus theta, then we could calculate the voltage across the components by for the resistor, VR is equal to R by IT, so we just multiply by R. VL is L di dt, so we have to differentiate the expression here and we get minus omega L Im sine omega t plus theta. If I want to turn this sine wave into a cosine wave, so it will match with the form of the current and the voltage across the resistor, that would be cosine omega t plus theta plus pi on 2 radians or plus 90 degrees. So either one you want to represent it as is okay. And for the capacitor, similarly, I will integrate this time. And I integrate IT, and then I get Im on omega c sine omega t plus theta. And again, converting that to cosine form, I now have minus pi on 2 radians or minus 90 degrees. So that tells us already the phase shift between the inductor and capacitor voltages are 180 degrees apart, or they're totally out of phase. So if I had to use this to find the voltage in the circuit, I'm going to do the same thing that we always do for transients or for DC circuit analysis, this is no different. I'm going to find the voltage around the loop, so Ri plus L di dt plus 1 on C integral between 0 and Ti t dt. And when I substitute the current, remember the current was Im cosine omega t plus theta. When I substitute that into this equation here, then I end up with this. And you could see that is very complex. It's the sum of 3 different sinusoids, each with different phase shifts. So it's not an easy thing to go about doing. It will be a very long, tedious calculation. So instead of going through this path, we could use phasors, and a phasor is a transform, just like we had the Laplace transform, and we were taking it from one domain to the other. The phasor, you could think of it also as a type of transform. It's a different representation for the same problem. We are not transforming the equations in the way we did with the Laplace we are just using a different representation really. So it's strictly speaking, it's not really a transformation because it's exactly the same equations, just in a different notation. So let's look at these voltage drops again. And this time we're going to represent them in exponential form using Euler's identity. And if you remember Euler's identity, it says e to the j omega, or let's just say e to the jx. E to the jx is equal to cosine x plus j sine x. So that is the identity we're going to use to represent these things in exponential form. So cosine omega t, the cosine term here, you could see is the real part of the exponential form. So if I look at the voltage across the resistor, Ri, which is Rim cosine omega t plus theta, that is the same as the real part of Rim e to the j omega t plus theta. And I can do the same thing for the inductor and capacitor. And when I find what they are in sinusoidal form, I could just look at the real parts for the exponential form. And of course, to do that, for all of them to be the real parts, I need all of them to be cosine, which is why I transferred them from sine form to cosine form earlier on. So additionally, I could remember that j is equal to e to the j pi on 2, and minus j is equal to e to the minus j pi on 2. So that I could convert these expressions here now to VL of t is equal to the real part of j omega lim e to the j omega t plus theta, and Vc is the real part of minus j Im on omega c. So now I have the three representations, 1, 2, 3, and I can add up these. If I want to do it for an RL, say we have Vt is equal to Vr plus VL. So I have the voltage across the resistor, which I just worked out, and the voltage across the inductor, which I just worked out. I could combine these two, and I will get Rim e to the j omega t plus theta plus j omega L Im e to the j omega t plus theta. Now that I have both of them with the same exponent, I could combine the coefficients, and I'll get R plus j omega L Im e to the j omega t plus theta. Now this is really a complex number. So if I look on the complex plane, real and imaginary, that is R and omega L. That point there is R plus j omega L. So I could represent that as e to the j alpha. So where this angle here is alpha. So I could convert this as well into, this part as well, into an exponential form. And then I will see that I could combine the exponents, and I get e to the j omega t plus theta plus alpha. So if I look at the total voltage at the end of the day, what is the final result, then I see that from my original current, which was Im cosine omega t plus theta, if I have two components R and L, then to get the voltage across these two components, what I do is I multiply it by the magnitude of the total impedance, which is Z, R plus j omega L, and I add the angle of that impedance. So I multiply it by this magnitude and I add this angle to it, and then I get I get what the voltage is across the circuit, and I didn't have to go and add three uh, sinusoids together with all with different phases. So this is essentially what the phasor notation is. So you could see it is a lot simpler because we don't have to go through any of the complex trigonometry. All we need to know is the magnitude and the phase. So if we're operating, and this is the important thing, on sinusoidal waves, the change is only to the magnitude and the phase, not the frequency. So if we go back, you'll see the frequency here remained at omega t, and only the phase components changed. So this means if we are doing this steady state analysis, as long as the frequency is constant, we could ignore the time component and we could just leave that totally out of the analysis. And we could form a more compact notation describing the wave just in terms of its magnitude and phase. And this is what the phasor actually is. So we could take this A cosine omega t plus theta, and we could turn it into simply A angle theta, because this tells us as long as we're all in the same frequency, this gives us the information that changes when we operate on the waves with other sine waves. Now in practice, we don't use the magnitude, we will use the RMS. So in practice, we will get A on square root 2 angle theta, and you'll see why this is done. It has to do with the calculation of AC power and so on. So in summary, this is a convenient way to represent AC sine waves. They essentially map sinusoids to anti-clockwise rotating vectors, but they're not really vectors, although they look like them. They're really sinusoidal waves, and the multiplication and addition of sinusoids is what you really accomplish here, not vector addition and cross products and dot products and so on. The magnitude of the phasor is the RMS of the value of the AC wave, and the angle of the phasor is the angle of displacement of the wave from a point of reference. So next time we'll take a closer look at converting to phasor form from the sinusoidal form.